Okay, so this video is going to cover chapter 1 in our textbook. More specifically, it's going to cover sections 1.1 and 1.2. We're not going to discuss really the content of 1.3 or 1.4. Also remember that there's PowerPoints on this topic that can be reached via my webpage. Much of the time in statistics, we are gathering data from a sample, and we're using the data from the sample to try to predict or estimate something about the population. For example, I'm really interested to know, since I drive about 45 miles to get to Cal Poly Pomona, I'm really interested to know what the average commute distance is for Cal Poly students, assuming that we were actually traveling to campus. So I'd like to know the average commute distance for Cal Poly Pomona students, but I don't want to talk to 24,000 students. So maybe I get a sample of 200 students and ask them how far they commute to Cal Poly, and I can find the average commute distance for my sample and use that as a prediction or an estimate of the average commute distance for all Cal Poly Pomona students. So this type of thing is done all the time in statistics. We're seeing this a lot this time of year on the elections. There's like 150 million registered voters, and everybody's trying to predict the election. But when they try to predict the election, they really only speak to about 5,000 voters at a time. No news agency has the money or the time to contact 150 million voters. Another example of why we sample from the population is because sometimes the sampling process or the survey process consumes the population. For example, someone's working in quality control at a bottling plant, and they need to make sure that the 12-ounce cans of soda are actually being filled with 12 ounces, not being underfilled or overfilled. So as the cans are coming off the production line, they're going to select a random sample of those cans, and they will be taken off to the side, and someone will be pouring the contents of those cans out and measuring them to see if the average contents is in fact 12 ounces. Or you can imagine another quality control scenario where they're pulling some of the cans aside to be taste tested for quality. So in those situations, once we open up that can to either measure its contents or to taste it for freshness, that can no longer be sold. So we can't do this testing on every single can in the population. Otherwise, we would have nothing left to sell. So we're kind of forced in that situation to sample from the population. And then based on what we observe from the sample, we make some inference or some prediction about the population. So then the big question is, how do we select such a sample? So we're going to talk about sampling methods. The simplest one to talk about is referred to literally as a simple random sample. So I'm going to use this example of 2,000 students at a high school for several different sampling methods. Suppose we have 2,000 students at a high school and we wish to select 200 of them at random to participate in a survey. We could place the names of all 2,000 students in a hat, mix them up, and then select 200 of them at random. This is the image of what a simple random sample would look like. Usually we don't put names in a hat. Some type of technology is involved, but a simple random sample, abbreviated SRS, gives every member of the population an equal chance to be in our sample. So, for example, here's a couple examples of how technology could be used. I've got 2,000 students on the campus. I can use my calculator to choose some random numbers. Let's just say that we've already assigned these students random numbers from 1 to 2000. This little function on my calculator will pick 200 numbers at random from 1 to 2000. So student number 1888 is part of my sample, and student number 1817 is part of my sample, and so on. Another way this could be done using technology, suppose I have the student names, I'm just calling them student 1 through student 32. Suppose I have all the students' names in my class. There's a couple different ways of doing this. I could assign every student a random number. So now every student has a random number, and then I sort my list of student names now according to those random numbers. Like this. So if I wanted a sample of 2 students, it's student number 23 and student number 2. If I want a sample of 5 students, it's those 5. So there's a variety of ways. You don't have to know how to do this on Excel. You don't have to know how to do this on the calculator. But the point is that there's a variety of ways that this can get done using technology rather than actually placing the names in a hat. But the analogy is placing names in a hat and reaching in and grabbing N of them. Now, there are sometimes things that are slightly undesirable about a simple random sample. If we take a simple random sample of 200 students, as I just described, it's possible that we might end up with 90 females and 110 males. And that might not be a desirable outcome. Some people might wish that the males and females were equally represented. So one way to do that is to take your group of 2,000 students, the population, and separate them or divide them into 2 groups or 2 strata according to gender. Select 100 females at random from the group of all females and 100 males at random from the group of all males. So you're still getting 200 students selected at random, but we've guaranteed that it's going to be 100 males and 100 females. And this structure, stratification, means that it's no longer a simple random sample, but it's still a very valid way of collecting a sample. Here's another example, still talking about stratified. You could take your population of 2,000 students and divide them according to grade level. So you got the freshmen in one pile, sophomores in another pile, or another hat, you could say, juniors in another hat, seniors in another hat. Reach in to the hat of freshmen and pick 50 of them at random. Reach into the sophomore hat, pick 50 of them at random. If we pick 50 at random from within each grade level, we still get 200 students total chosen at random, but now all the grade levels are equally represented. Sometimes it's hard to find the members of the population that you've chosen at random. So for example, I could have a list of all students at a school, and I could randomly select 200 students from that list. But now that the 200 students have been selected, I have to go and find where they are on campus. And that might be a little bit of a hard job. So instead, you could do something that's called a cluster sample. The students on campus are already situated in classrooms, let's say clusters of 20 students or so. So instead of selecting the students at random, we could select maybe 10 classrooms at random. So for example, if the 2,000 students are already located in 100 classrooms with, let's say, 20 students in a classroom, 20 times 100 would be 2,000. We could select 10 classrooms at random and then use all of the students in those classrooms, 10 classrooms, 20 students each. That would be our sample of 200 students. And they've still been chosen at random, but they haven't been individually chosen at random. The classrooms that they're in, or you could say the clusters that they're in, have been selected at random. Now, one thing to point out here is the students often get confused between cluster sample and stratified. So the big difference between these two scenarios is this. Up here, when I said I'm going to take my population of students and divide them according to gender, and then pick 100 males and 100 females, the students on my campus are not already separated by gender. They all have a gender, but they're not located in different parts of the campus according to gender. I have to take my list of student names and divide them by gender and then pick separately from each gender. So the students have gender, but they're not physically separated on the campus according to gender. With a cluster sample, the students are already in clusters called classrooms. Or if I was selecting soda cans at my local Stater Brothers, the soda cans are already in clusters, like 12 packs and 20 packs. So the students are already in clusters. I'm not having to put them in clusters. I'm not having to separate them into clusters. They're already in clusters, and I'm selecting the clusters at random. Convenience sample is a little bit lame, but it's sometimes done. Suppose we just stood at the school gates in the morning and selected the first 200 students that walk onto campus. That would give us a sample of 200 students, but I don't think anyone would consider that to be a random sample. So that type of sampling is called a convenience sample. One small step up from a convenience sample that involves a little bit of randomization is called a systematic random sample. Let's say we're still watching these students as they come onto campus. We pick a random number from 1 to 20. Let's say the random number we picked is 13. So the students start entering campus. We select the 13th student, and then we select every 10th student after that. So the 13th was chosen at random, but then after that, it's going to be every 10th student, the 23rd student, the 33rd student, the 43rd student, and so on. That'll still give us a sample of almost exactly 200 students and some randomization to it because the first student was selected at random, but then everyone after that first student was selected in a systematic way based on the first random number. Another thing that you could do is you could make an announcement on the PA system saying, attention all students, we're going to do a survey that we would like you to participate in, and those who would like to participate in the survey, show up at the gym during lunch. So in that situation, the students who show up to participate in the survey are doing so voluntarily, and so this would be called a voluntary response sample. If you think back to example 1, when I wanted to know the average commute distance for Cal Poly Pomona students, there's 2 different types of averages going on there. There's the population average, the average commute distance of all Cal Poly Pomona students, which is what I really want to know, but I don't have the time to talk to 24,000 students. And then there's the sample average, the average commute distance of my sample of 200 students. Once we've spoken to the 200 students, the sample average is easy to calculate, but we're not going to talk about calculating averages until chapter 3. But the point is that there's an average for the sample and there's an average for the population, and we need to keep those 2 different averages straight. And so there's a little bit of terminology we have to be familiar with. Numbers like this average that describe the population are called parameters, and numbers that describe a sample are called statistics. So we have population parameters and sample statistics. Okay, so now we're going to turn our attention to different types of data. So the two broad terms are quantitative and qualitative, which are also sometimes called numerical and categorical. A lot of data that we collect can be represented by a number. For example, a student's commute distance is just some number of miles. But there's also plenty of valid data that's worth collecting that does not lend itself to be represented by a number. For example, a student's mode of transportation. How do they get to school? That's not a number. Or a student's major. That's not a number. Data that can be represented using numbers is numerical data, also known as quantitative data. Quantitative, like the word quantity. Data that cannot be represented using numbers is categorical data, which is also called qualitative data, like the word quality. And both of these broad classifications of data can be broken down further. For example, sometimes numerical data consists of numbers which can be listed. For example, the number of children in a household. I know the possibilities there. The number of children in the household could be 0, it could be 1, it could be 2, it could be 3. I could actually list all the possibilities for number of children in a household. But other times, numerical data consists of numbers which can literally be any number on the number line or any number within a certain interval. For example, a person's weight. I can't list all the possibilities for a person's weight because a person could weigh 150 pounds, or they could weigh 151 pounds, or they could weigh 150.73 pounds. I mean, literally any number is possible as long as I have a scale accurate enough to measure it. So numerical data where only certain values are possible and those values can be listed is called discrete. You can often think of discrete data as being represented using integer values, like the number of children, for example. But continuous data is numerical data that could literally be any number, a length of time, a certain velocity, a person's height, a person's weight, etc. Categorical data sometimes allows us to put the data in some type of logical order. For example, on the homework, you'll see a problem about motion picture ratings, G, PG-13, PG-17, R, and etc. So even though those movie ratings are categories, there's an order to them. Or you could talk about the grade that someone earns in a class, A, B, C, D, F. Those are categories, but also there's a natural order to them. So categorical data that can be used to put items in order is referred to as ordinal data, but qualitative or categorical data that is in name only and does not lend itself to any kind of logical ordering is referred to as nominal data. So that's about all you need to answer the questions in Chapter 1 on Homework 1. I just wanted to show you real quick that you can access PowerPoints on this data by going to my webpage, which is cpp.edu/JC You can go there and click on a Stat 1200 class, and then click on PowerPoints, and you can bring up a PowerPoint presentation that will talk about all the stuff we just discussed: simple random samples, convenience samples, stratified random samples. Everything we just talked about is in one of these first two PowerPoints, either 1.1 or 1.2. Okay, so that's all you need to know for Chapter 1. After watching this video, you should be able to complete the Chapter 1 homework.